if you had like a sentence with 100 tokens in it, do you have 100 embeddings that you're putting in there?
Exactly, yeah. And what this lets us do is sort of pack this new context window with the greatest granularity possible.
All right, welcome everybody to Archive Dives with Oxen AI, where each week we dive into interesting research papers in AI and ML and try to tease out their key insights that we can apply to our own work. Today, we're diving into the Unlimiformer paper by a team at Carnegie Mellon and have the pleasure of having the lead author, Amanda Bertsch, here to discuss her work. We've been getting more and more authors showing up to the dives, and it's been fun to be able to hear about their practical learnings in the field and what they're working on next. It's a live on Friday event, and so it's kind of a unique experience for the community to show up and ask what's on their mind too. So today, the Unlimiformer paper is from last year. Amanda said they finished the work kind of in January, and it's all about extending the context length of LLMs and specifically transformers. It was accepted as one of the papers in NeurIPS, which has a high bar for quality work. And having an LLM understand long context, such as an entire book or your entire code base, would unlock a lot of interesting use cases. And Amanda and her team had a clever way of extending this context. So with that said, Amanda, I'll let you take it away.
Great, yeah. Thanks so much for having me. As Greg mentioned, this is work that is maybe a little bit older. So we finished this sort of end of 2022, beginning of 2023. And so I'm going to kind of talk through both the kind of what happened in this paper, the work this was inspired by, and then also a couple of things that have happened in the long context space since this, kind of following along this thread of doing a attention time retrieval to do better long context. But I'll start with the setting which is in the paper, which is this idea that maybe we have this relatively small encoder decoder model. We'd really like to be able to fine tune it for our tasks downstream, and we'd really like to be able to use it for inputs that are vastly longer than the pre-trained context length. And to sort of put this in perspective, maybe a motivating use case here is something like book summarization. So if you have an input that's 500,000 tokens long, and for context, this is about the length of the first Game of Thrones novel, you sort of can't just naively put this into your context window, right? So what do you do if you have this input that's 500,000 tokens long and a model that has a pre-trained context length that's grossly smaller than that? A really common approach in more classical NLP is to do some kind of hierarchical summarization, right? Summarize a couple of paragraphs together, summarize your paragraph summaries into a chapter summary, summarize your chapter summaries into a book summary. But if you make a mistake, if you propagate an error, that's going to cascade all the way down to your final summary. And if there's information that maybe doesn't seem relevant with the paragraph or two of context around it, but turns out to be critical later on, which is a pretty common case in a sort of complex narrative, there's no way to go back and sort of reconsider that context. So what could you do instead? Maybe you could just use a model that has a context window large enough, right? In the last couple of months, this has become sort of feasible in a way that it wasn't before. But if you're going to run this kind of thing locally, you're going to be paying a huge computational cost to do that sort of attention over 500,000 tokens. And that's even if you can find a model that can do this locally. There's not really a lot in the open source space that can handle a 500,000 token context. You could call out to an external model, but there's not really a lot of options to fine tune something like Gemini. And maybe you have some data that you're not really comfortable calling an API function with. So what can you do instead? And what we do in this work is, rather than focusing on extending the context window, we take this pre-trained context length as a sort of fixed limitation. We're not going to try to extend the number of tokens we can process at a sort of fixed point. Instead, we're just going to try to cycle through the context that we're processing over the course of decoding. So I'll talk through sort of what this looks like during inference as the modifications to an encoder decoder, then talk a little bit about sort of the more technical details that actually make this work, talk a little bit then about training, and then at the end, how maybe we could apply this to a decoder only model as well. So in this encoder decoder case, let's say we have an input that's 6 tokens long. And we have a model that has a pre-trained context length of 4, right? What we do is we take this input and we chunk it into these sort of sliding windows of context, and we're going to pass each of these chunks of 4 tokens through the encoder separately. This is fine because our encoder can fit 4 tokens at once. Then we're going to take sort of a well-contextualized embedding for each token and store it into this data store at the end of the encoder. So now we've passed a couple of things through this encoder, and we've gone from 6 tokens here to 6 sort of well-contextualized embeddings on the other side. If you were doing normal inference with this model, you'd pass 4 tokens through, you'd wind up with 4 embeddings on the other side. Then at the cross-attention side, usually you would cross-attend to this output of the decoder, right, at each individual layer. But we can't do that because we have more embeddings here than fit in our context window. So instead, at the point that we would usually perform cross-attention, we query into this data store where we've stored these embeddings. We retrieve a subset. So in this case, we retrieve 4 embeddings to attend to. And then we treat that as the effective context window for that attention head in that layer at that decoding step. And what this lets us do is, over the course of decoding, each head can cycle through context as we go. So for even a relatively small model, BART base has I think 6 decoder layers, 12 or 16 attention heads per layer, 1024 context. You can cycle through about 100,000 tokens at each decoding step. So if you're decoding a sentence or 2 of output, you can see more than 1 million potentially unique tokens in the course of contextualizing, in the course of generating that output. I'm going to step into a lot more detail on this, but I want to pause here because I see a few things in the chat. If there are any questions on sort of the general direction we're going to go.
So I had one question here for the size of the chunks that you're putting into the vector data store. Is that a configurable size, and what did you pick for the paper?
Yeah, this is a really good question. So we are going to, different from some kind of prior work in this area, like something like retro, we're actually only using this chunking on the input side of the encoder. Once we pull embeddings out of here, we're going to treat each of these embeddings completely separately from the others. So
if you had like a sentence with 100 tokens in it, do you have 100 embeddings that you're putting in there?
Exactly, yeah. And what this lets us do is sort of pack this new context window with the greatest granularity possible.
Cool. And then I think you said that you contextualize each one of them. So are you taking, like, if you had 100 tokens in the window and you're on token 4, are you combining the embeddings of the tokens around it at all, concatenating them, or is it just the embedding for that one token?
It's just the embedding for that one token, but what we do on the input side here is we ensure that every token that is sort of in the middle of our long input to begin with is passed through the encoder with both left and right context. And so over the course of passing it through the encoder layers, it'll be contextualized with respect to the tokens nearby it in the same way that the model usually does this. And that's sort of the only reason we're doing this kind of chunk encoding trick on this side here is so that we don't wind up with a token that is originally in the middle of the input, but once we get to an embedding, it only has like maybe context from one side or the other because it was on the edge of a chunk.
Cool.
What you're retrieving, Amanda, from the data store is actually vectors, right? Or token? You're retrieving vectors, right?
Vectors, yeah.
Okay.
So these are, to be really specific here, it's the hidden states of the last layer of the encoder, which is usually what would be in the window when you cross-attend.
Okay, thank you.
Cool. So let's see. To step into this in a little more detail, I think maybe the first clear question here is, how do we choose what we're going to retrieve? Like what is this query that we pass into the data store here? And this method is fully non-parametric, so we're actually just going to use what the model already has here, and we're going to use the cross-attention. So this is a part of the normal cross-attention equation. This is the part that determines how much each individual embedding is weighted in the attention computation. And so here we have the hidden states from the decoder. We have the hidden states from the encoder, this last hidden layer. And then we have these weight matrices for the queries and the keys that determine sort of a layer and head specific attention, right? This is the QKT, which is sort of the weighting part of the attention. What had been previously done in this area is if you wanted to add some kind of retrieval or some sort of memory to your model, you keep a data store of keys and you keep a data store of values. You'd sort of search into your key data store to determine what like individual keys you should pick, and you'd retrieve the values that correspond to those. This is sort of the reasonable first thing to do, but the problem here is that then you need to keep a data store for keys and a data store for values for each individual head you want to apply attention at. And so previous work in this area had only been able to consider sort of a small, like augmenting of the model with like a little bit of retrieval, maybe a layer, maybe half a layer, because you need to keep these data stores. And if you're storing 500,000 embeddings times 2 times the number of layers times heads, you're adding up your memory requirements pretty quickly. What we did instead is this sort of dead simple in retrospect rewriting of this equation. So you can fully factor this out so that you have the encoder hidden states by themselves. You keep a single data store of these hidden states, and then you just reproject the attention query for each head. And so this is the part of the attention that determines how much weight we're getting. So what we're going to do here is we're going to use a cosine similarity based retrieval to find the sort of reprojected queries that maximize similarity with these encoded hidden states, which represents the individual embeddings that would have received the most attention if we could attend to everything. So another way to think about this is by sort of, you could compute attention over all 500,000 tokens, and then you could just zero out all but the top 1K or 2K or 4K, however many fit in your context window. And this retrieval mechanism is just a sort of more efficient way of doing that. So this is sort of mapping this back onto the diagram we were just looking at. This is the decoder hidden states coming into the layer. The encoder hidden states are sort of this collection of embeddings we have in this data store. We'll reproject these decoder hidden states with this head specific attention. So this is specific to the head, specific to the layer. And this will give a set of retrieved hidden states that would have maximized the attention weight. Then we, rather than computing sort of cross attention with a fixed set of encoder hidden states, we compute it with this retrieved set of hidden states. And the rest of the model continues as normal. So this is how we sort of efficiently are able to attend to a different context window at each individual head. The way we do this search, you see the word KNN here, you can maybe guess, is through a vector database software. The particular one that we use for this is a product from Meta called FICE. And the nice thing about a software like FICE is that you can offload this data store of embeddings to CPU or even to disk, and that you can, with the cost of a small approximation in this search, do this kind of search in sublinear time. And we found that in practice, actually, approximating this search doesn't lead to any degradation in performance downstream. So we use a sort of approximate KNN search to do this selection of the attention window.
And it doesn't it doesn't lead to any. How could that be true, Amanda? It doesn't lead to any. Is that because it's linear, or?
I think there's two things going on here. The first is that, like, I think if maybe if you look at like the perplexity, you would see like a very small up or down. If you're looking at something kind of as coarse as the outputs, which is what we were looking at here, like does the output generated change? It doesn't make that much of a difference to maybe retrieve one or two slightly different things for each of these context windows. And the other one is that there's a couple of really interesting results in KNN LMs where rather than doing this at attention time, you're doing this in the last layer right before you sample what you're going to generate. And there's some evidence there that doing an approximate search is actually more effective than doing a exact search. And I can link that paper after. But the idea is that there's something useful in this sort of regularizing.
Cameron, were you asking about the performance in terms of like throughput?
Yeah.
Oh, sorry. The performance in terms of throughput is better with the approximate search.
Because you have less, because of that K parameter
Because it's
of how
linear,
many you're
not
returning.
quadratic.
Because it's linear, not quadratic, but it's actually sublinear because they do this sort of nice approximation where you group the sort of search space and then you search in sort of chunks. This is a detail of the FICE implementation. They use something called Voronoi cells to do this kind of sublinear search.
Okay, but the question that you were answering was interesting too.
Sorry, yeah, I misunderstood.
No, it's okay. I like both the answers.
Yeah.
Cool. And then Mike, you had a question as well.
Yeah, regarding FICE, are you using like vector quantization product? I know FICE has several quantization methods available.
Mm-hmm. Yeah, we didn't try quantizing actually, although that would be interesting to look at. We used just a trained, I want to say, I can pull up the exact name. I think it's in the code too. But we used just a trained index without quantization.
Cool. And then Alex, you had a question?
So related to the throughput comment, when you have the data store, does it have any effect on, well, so I guess one, where are you storing that? Is that on GPU memory, or is that in system memory, or is that on disk?
Mm-hmm.
And based on that, does the memory access have any influence on like the overall tokens per minute in terms of training or in terms of inference?
Yeah, this is a great question. During training, we're actually not going to use this data store at all because it's not differentiable, the data store operations. During inference, it makes a huge difference. So the experiments and the sort of timings that we present in the paper, because we're using relatively small models, we can use sort of the best case where you keep the data store and the index on the same GPU that your model is on. It's a little bit slower if you have to move it to a different GPU. It's a little bit slower if you have to move it to RAM. And we actually never tried moving it to disk. But this is because you only need one of these embeddings for each token in the input. It's not huge. I mean, it's fairly large, but compared to the size of the model, it's actually not that much memory.
Cool. And then one just kind of like intuition type question. I usually think of like the attention mechanism or cross attention as, you're looking at each token from the keys and each token in the queries, and you're trying to kind of say, like, if you had the word fly and you're trying to disambiguate it throughout the context, you're trying to look at like which tokens I should attend to try to give me more information of whether this is fly the bug or fly like as in travel in an airplane.
Mm-hmm.
And when you do this KNN search, how are you still maintaining like the position of the words when you return the top K of what to attend to?
This is a great question, and this is like one of the real complications to applying this kind of thing to decoder only models. So the sort of like a little bit unsatisfying answer for encoder decoder models is that the decoder hidden states, this concept of position here doesn't change at all. Right, we're not swapping out what's in the decoder output, and so the decoder is still sort of tracking position in some sense. The encoder hidden states, these have all kinds of positions, right? And the position is added before you go into the encoder. And because we're encoding in chunks and then just stripping these embeddings and placing them individually and packing them in different orders, they're all jumbled in all kinds of different orders. There's sort of a vague sense that like there's only a few things that have the very first positional embeddings and only a few things that have the very last, and everything else is sort of vaguely middle-ish. But if you were able to actually pull the positional embedding of each individual embedding here, they wouldn't be in a sort of meaningful order. The thing that kind of
it's kind of like a bag of words. Like
Yeah,
it gives you some bag of words context, kind of.
the thing that saves you a little is that these are passed through the encoder. And so like each embedding has some sort of weak knowledge of like, what were the tokens right before this and what were the tokens right after this. And so there's some sense of order there, but it's not the same kind of satisfying like numbered order that the model originally had.
Got it. Cool. Yeah, one more from Mike, and then we'll move to the next part. Sorry, Mike, you're muted.
Okay. So since you mentioned position embeddings, and anybody who's known me for a while, right here around here knows I have a burning, probably irrational hatred of position encoding.
Oh, we should
have,
talk. Yeah.
have you tried anything with Nope on this? And just right out of the gate, this has me thinking like the index itself gives it can't even say implicit, but explicit position information.
Mm-hmm. So the index itself gives it explicit position information. What do you mean by that?
In the data store. I mean, since you're just taking the input and indexing it sequentially, right?
Oh yeah, you could look at like the numbering of the tokens in the index and actually get that information.
Yeah, so you're essentially getting ape for free.
But the model doesn't see that though. So once you pack it into this retrieved hidden states, you have really no concept of what ordering things came in before. And we do generally try to sort things by the order that they were in the index, just because it seems like the principled thing to do. But in an encoder decoder, it doesn't seem to make a whole lot of difference if you do that. In a decoder only, I think if you had a model pre-trained with Nope, this would be sort of a better case to apply this at. The problem with a model pre-trained with Rope is that this query step is dependent on the distance between the query and the individual embeddings in here. And so you have this weird distance dependence that practically we ignore because there's no way to sort of efficiently do this search if you factor it in. But it means that there's like an even more approximate retrieval here. And I think this is one of the reasons that this is not quite as effective on a decoder only. But yeah, Nope unfortunately does not work on encoder decoder models, at least not on the encoding side.
Yeah, there are a few papers who I think push that, but they're few and far between. I think it's one of the severely underexplored areas of language modeling.
I thought that the reason that Nope works at all is the sort of dimensionality of the softmax and the ability to count how many tokens were previously in the context.
That and the causal mask definitely helps a lot too. But there are just a handful of papers that actually explore it. It definitely works better for decoder only.
Oh, that's really interesting though. I would love to see that if you have a reference.
Okay.
But, cool. So now we've got the context window. So you could do this at inference time only, right? You're not adding any additional parameters. And in practice, actually, this has a sort of modest improvement over the base model if you just toss this in at inference time without any additional training. But particularly in this sort of setting we were considering at the time, you're probably fine-tuning your model already for your task. And so it would be nice to fine-tune it with some awareness of what it's going to be doing at inference time. And the big question, if you're going to fine-tune with a method like this, is what does backprop look like? Like how are you backpropping through this kind of strange sort of non-differentiable operation down here? And the first thing you have to do here is, rather than a data store, you need to keep an array of these embeddings. And you can still do this sort of chunk encoding. You just need to keep the computational graph for each embedding that you plan to potentially backprop through. And then you don't want to backprop through everything all the time because you're not using every embedding all the time. So the question is, how do you sort of choose these retrieved hidden states? And there's a couple of different options here. The first is to do sort of the closest thing to what would happen at inference time, which is to compute attention scores across this array of embeddings, zero out all but the top K, and then when you backprop only through those top K. There's sort of, the advantage here is that this is very similar to what actually happens at inference time. The disadvantage here is that you're sort of backpropping uneven numbers of times through all of your inputs, which is a little bit strange. And you're also at sort of only seeing the things that the model already believed should have high attention weights, which if the model is wrong, or maybe you're training the model to only expect to see inputs that are extremely relevant at test time. And this is sort of not great if you have any kind of noise in your data. The other extreme here is to just randomly select a subset to pass through to the decoder at each step. This is the sort of nice idea that maybe you train your decoder to sometimes not pay as much attention to everything in the context window, right? You're introducing a little bit of noise. But then this also has a kind of weird property that, you know, maybe when you do attention at test time, you'd expect that your inputs are sort of more relevant on average than just a random subset. So the other option we try here is to just alternate between these two strategies, generally just alternating per epoch, and this works also quite well. That's sort of the gradients perspective of what we do at training time. There's also sort of an inputs perspective, because now you need to keep an array of embeddings and their full computational graphs. And this adds up your GPU memory pretty quickly. So if you're looking to stay sort of training only on a single GPU, you have some kind of limitations to your input here. And to sort of talk about what this looks like, you know, this kind of goofy example where maybe we're trying to train on summarizing Jurassic Park. So in a normal training paradigm, you would chop off most of your input. During training, you would sort of chop off most of your input during early stopping or validation, and you would chop off most of your input during test time, because you simply can't fit the whole book into your context window. The unlimiformer only at inference time setting, you're sort of training with these chopped off inputs, you're doing early stopping with these chopped off inputs, and at test time, you're showing full inputs. There's a sort of compromise setting here where during training time, maybe we don't want to introduce the extra compute requirements that you'd need to sort of train with long inputs, but we want to do our early stopping with the expectation that we're going to be applying unlimiformer. And so the training cost here is the exact same, but the validation cost is slightly higher because we're going to apply unlimiformer when we calculate our validation accuracy to do early stopping. And this, in practice, chooses like a very slightly different checkpoint for the model. This leads to sort of slight gains, and it costs very little. There's also the option of training with a longer input. And here the input length is still bounded at training time because we have to consider how many embeddings and how much computational graph we can fit into GPU memory. So we're actually going to train on only sort of a subset of the book still, but a much larger set than we could do before. Does that sort of make sense? Those sort of three classes of training time settings?
Yep.
Yeah. Perfect.
So I'll talk through a few results in this, and then we should have some time to talk about decoder only cases. So this is a couple of different data sets we consider here. This one in particular happens to be TV show scripts, mostly from Friends, a little fun fact. And here, blue represents the base model, red represents the inference time only setting, yellow represents the inference time plus early stopping setting, and green represents the training time setting. And I think this is generally the alternating setting, although in the paper we mark which one it is. And you can see here, this is sort of the classic the method works graph, so you can see performance increasing with our sort of additional awareness of unlimiformer. The same
Can you
trend.
talk a little bit about the Rouge scores and the Bertsch scores, just like intuition about what they are?
Yeah, with the sort of caveat here that long context and generation eval is really hard, and I don't think any of these are really great metrics. Rouge is a classic summarization metric, and this is looking at n-gram overlap between a gold reference and the generated reference. So Rouge 1 is going to be a sort of F1 score of unigram overlap. Rouge 2 is going to be bigrams, pairs of words, and Rouge L is going to be the longest common subsequence between the two. And so Rouge was sort of the most semantic maybe of these three. BERT score is using BERT as a scoring model, looking at sort of similarities between outputs.
Similarities of the embedding space, or?
Yeah, in the embedding space. So the idea is you sort of embed your gold in your generated reference, and you sort of look at their similarity according to BERT.
Cool. Cameron said Jody and her had to calculate Rouge L by hand last week, so they are super familiar with it.
Oh my gosh, that's
God,
one step further than me. What was that?
Thank God it's straightforward math. It's just simple division.
Yeah, there's a really interesting paper about implementations of Rouge by different Python packages, and it turns out there's actually, across like the 3 or 4 most common packages, a couple of subtly different implementations. So you can run Rouge from like 3 different Python packages and get different numbers, which is not great.
Oh no, not great.
So a real like always run your baselines yourself kind of situation. That paper is called Rogue Scores. It's really cool. But
cool.
So that's SumScream. GovReport is government reports, also looking at about 10,000 words is the average input length. So this is maybe in the like 16K tokens range. Back in 2022, this is what we called long context. But of course, we also don't want to evaluate just on these. We also want to evaluate on some sort of longer stuff. And so we'll look at books in just a second. But before we do that, it's sort of not fair to just compare against BART. We should also compare against some sort of longer context models that were already out there at the time. And so now in this, on this graph here, the blue line is still BART, just as it was before. The green line is still training with unlimiformer, but these red and yellow have been replaced with 2 other long context methods. So SLED is a really interesting encoder-decoder method where you encode the inputs in sort of sliding chunks, and then you perform fusion and decoder. And memorizing transformers is an older retrieval method where you perform a sort of retrieval augmentation style step, like unlimiformer does, but instead of sort of using your full context to cycle through retrieval, you do this at a single layer of the decoder. And so then we sort of said, all right, like this is really satisfying, but we want to look at sort of a much longer context. And so we looked at book summarization. Here, book sum, the average input length is about 150K words. So maybe like 175K tokens, 200K tokens. And the base model here is shifted slightly to a model called Primera, which is a 4K context length, simply because with BART, it's only a 1K context. You couldn't really get anything really meaningful. And this I want to spend a little more time on because this is sort of not the usual story graph here, right? Like you can see it actually looks like our baseline is outperforming training with unlimiformer. Here, some methods are higher than others. It's not really clear why, kind of what is going on. And so we spent a while looking at this, and it turns out what's going on is kind of twofold. Rouge is a really not a great metric for long form output evaluation, and the average output length here is about 1,300 words. And so what you could read the 2 summaries and see sort of like the summary that is conditioned on the first 4K words of the book is almost meaningless, right? Like it mentions some characters that occur in the first chapter. It has no clue of what actually happened in the book because it doesn't see the book. But it hits enough of those neither of these models hit enough n-gram overlap to have sort of a like reasonable comparison here. Like there's so many different ways to write the summary of a book, and this is such a long output that the Rouge scores don't really distinguish between these 2 models almost at all. And so what we look at instead is a sort of entity mention metric called EntMent. And the idea here is that you want to include the entities from the gold summary in your output. Maybe we don't really actually care about if you get every turn of phrase right, but we'd like it to mention like the locations and the people that actually occurred in the book. And if you look at this sort of more fine-grained metric, you see really dramatic improvements from incorporating more context and from training with more context. And you also see this sort of nice trend where generally, with some caveats, as you increase the amount of context the model is allowed to attend to, the entity recall goes up. So this red line here is the base model, which only has, I think here we're using BART, so we only have 1,000 tokens of context. And here, the x-axis represents increasing the amount of context we allow the model to attend to, from only 1K tokens up to 350K tokens. And you can see sort of generally increasing context increases this downstream metric. This little dip here is interesting, and I wish I had a really compelling answer for you here. There's a couple of examples in the test set here that are about 50K tokens long. And so there's no additional gain from scaling up context past this point for these examples, but there is some noise in the performance of the other examples. And so maybe this is causing some degradation.
Interesting. This is cool. I haven't thought much about evaluating summarization, but my background's kind of in like entity extraction, relationship extraction, sentiment, and all that, like in the classical NLP sense. And I'm wondering if there's even like a entity relationship recall metric that you could do, that it's like it mentions something about Bilbo and the ring connected, you know, through like a relationship. I don't know.
No, that's really interesting. We looked a lot at sort of factuality metrics too, but it's really hard with this length of input, and also with this length of output, like 1,000 token outputs. It's really hard to find sort of effective methods of evaluation. This entity thing is, we got the idea from medical summarization, where this is also a huge issue.
That makes sense. Cool.
And so then sort of the last thing from the paper itself is to talk about computational cost, which I think we got into a little bit earlier. But the cost that you have to pay to apply this method at inference time, so setting aside whether or not you trained with it, you'll pay additional cost in kind of a couple of different directions. You have to encode additional input over the base model. This is sort of, I think, really unavoidable. You have to pay a one-time cost to construct the data store and to train the data store to train the index if you want to use approximate retrieval. And then at each decoding step, at each attention head, you have to pay a cost to search into the data store to select your new window. The sort of nice property here is that if you actually look at trying to profile decoding cost for encoder-decoder models, encoding is actually a very small amount of the total cost you're paying. And this data store construction is one time. So while this encoding cost is linear, this data store construction cost is sort of O of 1, this data store search is sublinear. The overall effect, if you look at something like wall clock time, is actually sublog linear. And so this red line down here represents the wall clock time for running BART base with a 1,000 token input. This blue line here represents the wall clock time for running unlimiformer applied over BART base with inputs from 1 to 100,000 tokens. So you see these sort of one-time costs are really expensive in the initial case. You're paying more than twice the cost to summarize the same amount of input. But with 100 times more input, you're paying about 3.8 times the cost of the base model. So this is really sort of a nice scaling behavior. So this is the sort of set of results from the original paper. We can use a fixed context length model. We can use sort of minimal additional computed inference time, and also the possibility of offloading that storage to another device with some latency costs, with minimal additional time, and even sometimes with a little bit weaker performance without fine-tuning at all. So I have a few things to say sort of about decoder-only cases, but before that, I guess, are there any questions on the paper itself? Cool, I can keep going. So how do you apply this to decoder-only models? And there's sort of 3 different cases I want to very briefly touch on here. The first is if you want to take the unlimiformer method directly and apply it to a decoder only model. And there's a paper that does this that was at LREC last year. I haven't personally run their code, but their results look convincing. It looks sort of like a reasonable thing to do. Model, you're not cross-attending back to a single fixed encoder. And so what you do instead is you can construct this index layer-wise. You can treat layers, up to layer n as the encoder for layer n+1. You also then have the choice of applying this at every layer at only a subset of layers. And in practice, we ran a few experiments with this. And for big models, I think we were looking at Llama 1 or Llama 2 7B at the time. It's actually not super helpful to apply this sort of layer-wise index at anything below anything in the first half of the model. Applying it later and applying it only to a subset of layers seems helpful, which I think makes sense if you think about the sort of beginning of the model as doing the same part that the encoder would be doing in an encoder decoder. You also then have to worry about positional encodings a lot more. The solution that we had here, which I think is not super satisfying, is to retrieve without respect to position and then apply the positional embeddings afterwards, sort of retrieve a set and then recalculate attention with respect to the relative positions. And here we were using positional interpolation before it was cool. So we were sort of using fractional positions to represent a much longer context than the model was trained with. There's also sort of similar kind of retrieval flavored methods for long context. So Long Llama, I think, is a really great project in this area that uses a single retrieval layer, and fine-tunes this model with the focus transformer method, which is sort of similar inspirations to our alternating training, where they do some kind of contrastive training to learn what to actually retrieve at test time. So this is a really cool project in this space that I want to shout out. And then there's also the idea of doing this only at inference time. And there's a couple of really interesting works recently that have sort of taken this idea that maybe long context attention is choosing what to retrieve from the long context and really run with it. So LM Infinite and InfLLM, similar names, but kind of slightly different methods here, both use this concept of choosing what the individual head is most attending to and then kind of discarding the rest. So sparsifying your context in order to make long context generation sort of computationally feasible. And these both also introduce some really interesting other tricks to make this work. So yeah, thank you guys so much. That was a sort of whirlwind couple of shout outs to some really cool, more recent projects there. And this unlimiformer was joint work with these great folks. And then a shameless shout out that I'm also working sort of on long context and context learning more recently, if that's something that anyone is interested in. Nice.
Amazing, Amanda. That was a great explanation. It's super, super intuitive. And thanks for putting together these beautiful slides as well.
Thank you so much.
I'm going to kill the recording here and then we can kind of have a offline discussion. So if you're watching on YouTube, feel free to join us on Fridays. This is the fun part where we kill the recording and just chat afterwards. So see you guys.